Mount Saint Helens rises in a halo of ash and steam, a once mighty giant now sleeping uneasily. But could it be that something is lurking beneath its slopes? Rumours have been swirling among volcanologists and outdoor enthusiasts alike. Are cracks secretly growing in the flanks of this volcano, weakening its very core? Is a catastrophic slide with echoes of May 1980 on the verge of happening again? Imagine the north side of the mountain slipping away as magma pushes upward, the ground roiling like a shaken foam. Such questions raise chills. In a region where the past has seen tragedy, scientists are now scrambling to understand just how stable the base of the mountain really is. For communities near volcanic peaks, the most dramatic hazard is not just lava or ash, but the mountain itself unzipping. History has shown that entire volcano flanks can fail catastrophically, sometimes with deadly consequences. In 1883, a collapse of Krakatoa in Indonesia unleashed tsunamis over 100 feet 30 meters high, killing tens of thousands. More recently, in 2018, Anak Krakatau's flank collapsed and a tsunami swept into coastal villages, taking hundreds of lives. And on May 18, 1980, here at Mount Saint Helens, the north flank literally caved in. That ancient avalanche of rock emptied a portion of the mountain like a sinkhole of earth, triggering a sideways blast that scorched the landscape. 57 people died in that one day, and the blast sent an ash plume to the stratosphere taller than 80,000 feet, nearly 25 kilometers high. The lesson is stark. Flank collapses can be more deadly than fiery lava flows. Today, any whisper of weakening flanks at St. Helens raises alarm bells. Could this iconic volcano be gearing up to repeat history? Mount St. Helens stands sentinel in the Cascade Range, straddling the volcanic arc that runs from British Columbia down to California. It is a stratovolcano built by the slow subduction of the Pacific tectonic plates beneath North America. Layers of ash, pumice, and lava domes have piled up over hundreds of thousands of years, making a classic cone until 1980. Geologically speaking, this is an explosively capable volcano. Its magmas are high in silica, making them sticky and gas-rich. Repeated eruptions over centuries have reshaped the mountain. In fact, long before European settlement, Mount St. Helens had already blown its top on several occasions, building older versions of itself and leaving behind thick deposits of volcanic mud and debris that filled nearby valleys. Carbon dating of buried forests and lava flows shows major eruptions and collapses tens of thousands of years ago. In the relatively recent past, within the last few thousand years, giant pyroclastic flows and minor landslides remodelled its flanks time and again. This pattern of grow, collapse and regrow is a part of St. Helens's restless nature. By the spring of 1980, Mount St. Helens had been dormant for over a century, but deep within, the volcano was stirring. Seismographs recorded dozens of earthquakes beneath the summit, and satellite data showed the north side bulging outward by several feet over a metre each day. Geologists realised that an enormous mass of magma was intruding into the upper chamber. Unseen by the casual eye, the volcano's sides were straining like a wound-up spring. Then, on May 18th, a magnitude 5.1 earthquake struck just under the north flank. Instantly, the weakened slope gave way. In an astonishing second, the mountain's gigantic north side sheared off and began sliding downhill. This was the largest subaerial landslide ever recorded on Earth. About 2.8 cubic kilometers of hot rock, soil and uprooted forest thundered down at speeds reaching 250 kilometers per hour. Spirit Lake and the Toutle River Valley were buried by debris, averaging some 46 meters, 150 feet deep, in places as deep as 60 meters, nearly 200 feet. The slide exposed the magma beneath like uncorking a bottle of champagne. When that wall of rock collapsed, the magma and trapped gases suddenly expanded into the void. The result was a devastating explosion of ash, gas and incandescent rock, a sideways blast that swept northward and a towering eruption column that punched into the stratosphere. Satellite imagery captured an umbrella-shaped cloud billowing across the Pacific Northwest. Trees were knocked down over an area of about 600 square kilometers, 230 square miles, flattening forests like matchsticks. A raft of countless pine logs was tossed into Spirit Lake. In the minutes following the collapse, a cloud of hot ash raced across the sky at perhaps 300 kilometers per hour, carrying volcanic glass, rock shards and debris. Farmland downwind was buried in ash up to a metre thick, and airplanes all over the continent reported an ash plume up to 24 kilometres high. The mountain's summit lost an elevation of some 350 metres over 1,100 feet in one catastrophic blast, turning the once symmetrical peak into a horseshoe-shaped crater. In short, the collapse not only destroyed the north side of Saint Helens, but also set off an explosive eruption that few saw coming. Over 1,000 homes, 27 bridges and vast swaths of wilderness were obliterated. Most of those 57 victims had been caught in the avalanche and blast zone. That nightmarish day in 1980 was not the only time Mount St. Helens has changed form in catastrophic fashion. Geologic evidence shows that a similar collapse occurred about 5,000 years ago. Back then, an even larger volume of rock roared down the mountain, producing colossal surges of volcanic mud lahars far downstream. In that more ancient event, massive pyroclastic flows also blasted from the breach. Over hundreds of millennia, geologists have mapped older flank failures, some leaving behind open cliffs and hummocky debris aprons around the mountain. And smaller eruptive episodes in the 20th century, for example, an eruption in October 2004, followed by lava domes forming in 2004 to 2008, continued to tweak the crater, but without another full-scale collapse. Each eruption carries the potential for unstable slopes, but none since 1980 has unleashed a wholesale flank collapse. Still, the ghost of the past lies in the stratified layers and fault lines of the volcano. Underneath the surface, the plumbing of magma and hydrothermal fluids can alter the rocks. What once was dry and solid may have been softened to clays by steam and water or cracked by tiny earthquakes, weakening the very material holding the volcano together. The science of volcano collapse has advanced tremendously since 1980. Researchers now understand that flank failures are governed by a few key factors: the geometry of the mountain, the angles and orientations of fractures, and the pressures building inside. Think of it like a stack of blocks on an inclined plane. If the internal support shifts, the blocks can start sliding. At St. Helens, prior to 1980, the magma build-up had bent the volcanic edifice into a bulge. The internal fractures, especially a wet, clay-rich zone on the north side, became locked under stress. When the stress exceeded the strength of the rock, gravity took over. Today, scientists use the term slope stability to describe when the volcano's own weight becomes unsafe. What might cause a future collapse? The most common trigger in subduction zone volcanoes is renewed magma intrusion. When a new batch of magma rises and pools beneath the volcano, the rock is pushed outward again. This injection of molten rock is like pumping air into a balloon. Walls stretch, fractures open, and pressure builds. Geophysical measurements can detect this inflation. Tilt meters and GPS stations around Saint Helens would notice if the summit started bulging once more. In fact, before each of the smaller eruptions in 1980 to 86 and 2004, scientists observed this exact phenomenon. On top of that, fluids, steam and gases exsolving from the magma permeate cracks, raising the pore pressure inside rock. When fluid pressure builds, it counteracts the friction holding rock together, effectively lubricating potential slip zones. Water from rainfall or snowmelt can seep into the ground, especially into old crater lakes, and migrate downward. Some of it can get superheated in the hydrothermal system, converting to steam that cracks rock apart. If any rock is already heavily altered by hot fluids, for instance to clays like montmorillonite, it can be extremely weak compared to fresh basalt or andesite. Volcano hazard specialists have long pointed out that Mount St Helens is not as waterlogged or altered as some neighbours like Mount Rainier. Nevertheless, it does have a crater lake at the bottom of its new crater and old hot spring deposits in places. Magma often finds fault lines to exploit. At St Helens, more than a dozen major fracture sets were identified around the summit. Some of these are steep, slicing nearly vertically into the cone, while others are broad and shallow, aligned with old lava dome blocks. Both arrangements matter. Imagine a block of rock on a gentle slope with a nearly horizontal weak layer beneath. It may slip out like a sled. Or picture a block on a steep slope with a nearly vertical joint, and it could tilt and topple. In the latest research, computer models led by Penn State geophysicist Christelle Vautier are shedding light on this problem. Her team simulated thousands of scenarios in a range of volcano shapes and magma pressures. One key finding is that gentle slopes can be surprisingly prone to failure if magma intrudes right under the summit, lifting huge slabs off. Yet steep slopes with near-vertical faults can also collapse if magma finds those cracks. Topography, the real three-dimensional shape of the mountain, turns out to be crucial. In plain terms, if a volcano bulges, one side or the other might give way depending on its incline. Vautier notes that shallow dipping faults on broad parts of the mountain are likely slip surfaces under pressure, while even more vertical fault plains on narrow ridges are like breaking knives under stress. Such models do not yet say St Helens will collapse tomorrow, but they do pinpoint where to watch. They suggest where to put instruments. For example, if a flank is calculated to be most unstable when magma wells up, scientists might install extra seismometers, GPS receivers, or tilt meters on that flank to catch minute movements in real time. Are the flanks of St Helens really weakening now, in late 2025? Officially, the United States Geological Survey says no drastic signs are evident. Monitoring data indicate that the volcano's alert level remains at green, meaning normal background activity. No new bulges are reported, no unusual steam or earthquake swarms have been seen. As one recent USGS report dryly noted, occasional strong winds are stirring up the decades-old ash deposits, but there is no change in volcanic activity. The Cascade Observatory still emphasizes that the deep crater formed in 1980 actually makes a second giant flank collapse less likely for the time being. With the volcano's top breached and much of the unstable upper rock removed, scientists argue that something like the 57 fatalities of 1980 or the giant landslide of that day is unlikely to repeat in exactly the same way. Nonetheless, geologists who specialize in volcanic landslides caution that as long as magma is the driving force below, nothing is impossible. The models show that if a new batch of magma rises, it would attempt to push aside the same cliffs and faults that failed in 1980. The volcanic vent system under Saint Helens could reopen the path for a flank to break free. And some researchers privately wonder whether subtle signs might be overlooked without continuous attention. For example, between major eruptions, volcanoes can quietly deform by just centimeters per year. That is well below what satellites can easily see until an explosive episode begins. Small rock avalanches in the crater are common and typically detected only by seismic noise. Scientists could hypothesize if the volcano is quietly inflating by millimeters unseen by the naked eye, it might be edging closer to an invisible tipping point. Another angle of inquiry involves the material in the debris avalanche. During the 1980 slide, a puzzling amount of water suddenly burst from beneath the rock, raising Spirit Lake's level and generating a near 600-foot wave that swept over the lake's ridge and came roaring back as a surge. Could some similarly trapped hydrothermal fluids or crater lake water cause trouble if the flank were to fail again? The concern is theoretical. Today, a lake rests amid the rocky rubble inside the crater, a few hundred meters across. If a shock wave from below displaced it, small tsunamis within that confined lake might result sloshing water over the crater rim. But by itself it could not send lethal waves downstream, because the lake and ponds are too small to matter on a grand scale. The greater hazard would always be pyroclastic flows or avalanches hitting one of the river valleys. That scenario, igniting Mount Rainier like hot avalanches of ash and rocks down the Toutle River, remains the nightmare scenario if the volcano's structural integrity failed catastrophically. Thanks to modern technology, we are far more prepared than in 1980. An array of instruments surrounds Mount Saint Helens. Broadband seismometers pick up even the faintest shudder, tilt meters record slope angle changes at microradian precision, and GPS stations detect ground movements measured in millimeters. Continuous gas sensors sniff for a spike in sulfur dioxide or carbon dioxide from new magma. Satellites scan the volcano's surface for any subtle uplift or temperature changes. In recent years, these networks have only shown routine fluctuations, like minor thermal anomalies, typical steam and low-level tremors. In 2023 and 2024, only harmless rockfalls from the cooling lava dome were notable. A dozen webcams peer into the summit crater in real time. Every few months, scientists helicopter into the volcano's crater to recalibrate the equipment and scrape off dust, ensuring nothing goes broken. The new computational models from Penn State complement this arsenal of tools. Instead of just reacting to data, they try to predict where collapse is most likely to begin. In practice, this means identifying the weak spots of a volcano. For Saint Helens, it highlights the inner faces of the horseshoe crater and certain blocky lobes of the dome that were created in the 1980 to 86 eruptive sequence. If magma were to bluntly intrude under the summit again, these zones are logical candidates to fail first. By cross-checking model predictions with field observations, geologists could even run drills on evacuation planning. It is a sobering thought. Communities downstream, and tourists along Spirit Lake's shores might one day get advance warning if these models detect an accelerating slump. So, could the northwest face of Mount St Helens suddenly slide off in our lifetimes? Current forecasts lean toward caution. Given the volcano's present form, a cliff failure on the scale of 1980 is not considered imminent by most experts. But the planet is full of surprises. The flank is not going to crumble like old ruins without clear cause. It needs that cataclysmic input of energy from below. The truth is that no scientist can give a firm timeline for eruptions or collapses. The very nature of these processes is that a million tiny changes build invisibly until one day they cross the threshold. All the while, magnetic fields shift, rocks cry out in tremors, and the mountain sleeps fitfully. At base, what distinguishes Mount St Helens today from that fearful night of May 1980 is that it has already lost the part of its skeleton that was most unstable. The summit breach acts like an open safety valve, but if fresh magma ever breaches the roof of the chamber again, it will once more apply tremendous force on the remaining structure. The recent research simply reminds us, when that force meets weakness, whether a gentle fault plane or a towering wall of ash, the outcome can be instantaneous and violent. The mountains may appear eternal, but in geologic terms they can fail in a heartbeat. In the end, the answers seem to be yes, the flanks could collapse under the right conditions, but it is not predicted to happen imminently. Vigilance is the watchword. Geologists now have better eyes to see beneath the surface, but nature still holds a few cards close. For now, visitors and nearby residents can take some solace from the absence of urgent alarms from volcano monitors. Yet one cannot help but look up at St Helens on a quiet day and wonder how long until it next throws us a surprise. The volcano's legacy is clear. It will erupt again, and when it does, the way it fails will shape its fury. We may never completely rule out the risk of a flank collapse, but thanks to science, today we at least know the signs to watch for. In that silent watch lies our best hope to avoid a repeat of past disaster. The ground beneath us is alive, and so is this channel. If you enjoyed uncovering the hidden power of Mount St Helens, hit that like button, share this with a fellow explorer, and subscribe for more stories where geology meets destiny. Tap that hype icon so you're always first when the next seismic story drops.